Section 10.5.2 Different Length Tags. When the substitute for each tag is not the same length, you get into a variety of complexities. The length of each block can change, and the blocks may not end up aligned on byte boundaries. For example, a 32-bit block could become a 35-bit block. This means that Riva will need a means to separate the blocks. The simplest method is to transmit the length of each block. It might seem feasible simply to perform post-tag substitutions on a block until its length becomes a multiple of 8 bits again. Unfortunately, this potentially could take thousands or even millions of substitution steps, or it might never happen. The simplest solution is to encipher the entire message as a single block. The length of the message tells Riva the number of bytes in the block. Sandra just needs to add a 3-bit field to tell Riva how many bits are in the last byte, ranging from 1 to 8 bits. This could be placed at the start of the message, or it could be the last 3 bits of the last byte. The length field might require an extra byte. Here is an example of different length post-tag encipherment. Each prefix tag and its resulting suffix tag have matching underlines. It might look like you will need to shift the entire message each time a tag gets removed from the front. These shifts could be eliminated by keeping pointers to the first and last bit of the message. Each pointer will simply be an integer giving the location of each end. The low-order 3 bits of the pointer will give the bit position within the byte, and the high-order bits will give the byte position. Allocate a space 4 times the length of the message. Place the message at the start of this space and zero out the rest. To delete a tag from the front of the string, just increment the front pointer by the length of the prefix tag. To append a tag to the end, just shift the tag to the required bit position, and OR it with the last 2 bytes of the string, then increment the end pointer. Continue this process until you reach the end of the space. This means that the number of post-substitution steps depends on the message itself. That leaves just one shift to perform at the end to get the bit string onto the even byte boundary. However, this long shift can also be eliminated by telling your correspondent both the starting and ending bit positions in the first and last bytes of the message. This requires only 6 bits, which can be packed into a single byte and placed at the start of the message. I recommend enciphering this byte with a simple substitution so as not to give Emily the starting and ending positions. Also, be sure to fill the unused parts of the first and last bytes of the message with random bits. One question remains. Since Riva does not know the original length of the message, and hence does not know the original size of the enciphering space, how can she know when to stop deciphering? Riva does not know how many substitution steps were done, and she cannot simply allocate a space 4 times the length of the received message, because that may not be the same as the length of the sent message. Here's how. Riva knows 3 things. The plaintext message started on a byte boundary. The message ended on a byte boundary, and the enciphering space was 4 times the length of the original message. Riva can begin by placing the received message at the end of a space 5 times as long as the ciphertext message. That should be more than ample. Riva works backward until the 3 conditions are met, in particular until the distance from the start of the partially deciphered message to the end of the deciphering space is exactly 4 times the length of the message. This can only happen once. I suggest that you use 50 to 80 pairs of tags, with each tag 4 to 8 bits long. The expected length of the original tags should be close in value to the expected length of the replacement tags. About 1/3 of the replacement tags should be shorter, 1/3 should be the same size, and 1/3 of the replacement tags should be longer than the original tags. Don't insist on making every tag a different length from its substitute. Message characters should be represented as 8-bit bytes in a well-mixed alphabet. If the expected length of the tags is T bits and the length of the message is L bits, then at least 3L over T substitution steps should be made. That is, you go through the whole message 3 or more times. The final bit string, including the length indicator, should be converted back into characters using a second, independent keyed simple substitution. If all of these suggestions are followed, then this cipher, called POST-DL, is rated 10. When you reach section 12.6, you will see that the POST-DL cipher does not meet all of the criteria that guarantee an unbreakable cipher. The reason it gets a 10 rating is that Emily does not know where in the ciphertext any given plaintext bit will end up. The position will differ from block to block, so Emily cannot set up a correspondence between the plaintext bits and the ciphertext bits, and thus cannot set up equations relating the ciphertext bits to the plaintext and key bits. Section 10.5.3 Multiple Alphabets. There are several things you can do to strengthen a POST-tag cipher or a Huffman substitution cipher. We have already looked at having multiple rounds of substitution. Another trick is to use multiple alphabets. Each alphabet will consist of a set of tags with the prefix property and the corresponding set of replacement tags, which must have the suffix property. You can simply use the multiple alphabets in rotation, or you can use a keyword to select among them. If you are doing this by hand, you will not want more than 2 or at most 3 such alphabets, so I suggest using a numeric key like 0110111. These ciphers, which may be called polypost and polyhuff, are rated 4 to 8, depending on the number of rounds, the number of alphabets, and the key length. Section 10.5.4 Short and long moves. So far, we have assumed that when a POST tag has B bits, these B bits are moved to the end of the block. However, it is possible to move fewer than B bits or more than B bits. For example, you could move B-1 bits, leaving 1 bit to be substituted again as part of the next tag. This makes the tags overlap. The advantage is that it conceals the boundaries between the tags. The disadvantage is that it requires more substitution steps per round, making the cipher slower. Conversely, when a POST tag has B bits, you could move B+1 bits to the end of the block. This leaves 1 bit unchanged, and that bit is always the last bit in the block. This is not a serious problem if the cipher has multiple rounds, so that the unchanged bit will probably be substituted in some other round. There is still a chance that some bits will pass through this cipher intact. This is not a serious weakness if Emily cannot determine which are the unchanged bits. Bits are anonymous. There is nothing about any bit that says, "This bit came from byte 5, bit position 2" in the plaintext. Finally, the number of bits that are moved can be made independent of the length of the tag. You could have a table that tells the number of bits to move. This can be less than, more than, or the same as the length of the tag. You can have several of each. When the number of bits moved is different from the length of the tag, the suffix property no longer applies to the set of substitute tags. Instead, the set of bit strings that are actually moved must have the suffix property. For example, if the tag 0110 is replaced by 1101, but 5 bits are moved, then the set of suffix strings must include both 11010 and 11011. Section 10.6 Fractionation in other bases. So far, this chapter has discussed monem-binem in base 5 and Huffman and POST substitution in base 2. Variable length substitution can be done in other bases as well. For hand enciphering, it is better to do Huffman substitution and post substitution in base 3 or base 4 than in binary. However, variable length substitution can be done in any base, even oddball bases like 11 or 13. This can give you extra substitutes, which can be used for homophones or for encoding bigrams. When you work in base 13, you can use any 13 of the 16 hexadecimal digits for substitution and leave the other 3 digits as nulls. If done well, so that all 16 digits have roughly equal frequency and distribution, Emily will not be able to tell the valid digits from the nulls.